Next, we're gonna have Priscila Silva from University of Massachusetts Dartmouth talking about covariate resilience modeling.
Good afternoon. My name is Priscila. So today I will talk about resilience models. So what resilience is, I like to say that it's the ability to recover from failures, and it actually applied for many domains such as cybersecurity, cyber physical systems, economical systems, environment, and so on. So the lack of resilience is dangerous. So we can see, I have an example here. For example, a blackout that happened in 2003 due to a software error caused 45 million people in the US to go without any power for like 2 days. And also it caused from 4 to 10 billion of implications, and the mortality rate increased 28%. So because of that, common practice on resilience try to apply resilience metrics to see how resilient a system is and try to improve the next design of that system, okay? But sometimes a system doesn't have a second time. So that's why we came up with this research, because we are actually trying to apply mathematical and statistical models to try to track and predict how the performance changes over time. So resilience, the resilience ability that I said, it's actually divided in 4 states. So we say that a system needs to be prepared to a disruption, and then it needs to absorb the disruption to keep the most important systems alive, and then it recovers to a high level of performance again and adapt to the new environment. So we have in blue a canonical curve. So we usually see that in the textbooks. But in reality, so we have in red over there, that's what happens. So a system can degrade multiple times. And that's actually what we are trying to track and predict, okay? So we have a metric on the right side as an example. So that is the performance preserved, or we just call the area under the curve. So people try to track how the system was able to preserve the performance to improve the next design again. So like I said, we want to track that in real time to be able to change some activities that can actually improve the performance during the time. So I'm proposing 3 different models approach. So the first 2 are the bathtub-shaped hazard functions and mixture distributions. So by using those 2 approaches, I was able to track and predict single shocks. But like I said, that is not very much the reality. So we want to track and predict multiple shocks. So we have something that's called covariate models. So covariate is just different activities that can impact the performance of my system. And that's going to be the focus of my talk and my research, because it is able to predict multiple shocks. So that's why we should be using that. You're going to see my examples later. So the performance at time I call that P of I. It's just the performance of the previous interval plus the change in performance, which is called delta P. And delta P is actually what I'm trying to predict, okay, the change in performance. And then I'm using multiple linear regression to predict that. It's very simple. The equation is over there. And I have some variations like multiple linear regression with interaction of the covariates and polynomials as well. So you can see that the X over there in the equation is a covariate, and I can have M covariates, okay? Betas, beta naught and the other beta J's is just the coefficient, so it's going to be estimated through a technique, of course. But the most important thing is how we can identify the X's. So we should be able to identify what caused our system to degrade and what help the system to improve performance as well. So we need to identify those activities, and we need to be able to collect the data for a couple of intervals that we want, and then we estimate the parameters of the model. So I'm using maximum likelihood estimation for that. It's very simple to use, but we have any other techniques that can be used there, like Bayesian estimation as well. And after that, we need to validate the model. So we are using some goodness of fitness measurements to see how well we can track and how well we can predict the performance, the change in performance, right? We also use I-square adjusted to see how well correlated the covariates that we collect actually improve the model or degrade the model. So to give an example, I'm using a finance system because it's easier to find this data. It's very available, and we can think in a better way about the covariates as well. And we can learn a lot from finance as well. That's why I'm showing this. Okay. So P, remember that P is the performance that I said. So I'm considering P as the number of jobs in the US. And this is a recession that happens in 1980 due to the energy crisis that we had. And you can see that I was able to collect 8 different covariates over there. And the bold ones are the good ones that I was able to select through a forward selection technique. And I'm highlighting over there as well as a negative or positive sign just to represent if it was a covariate that impacts in a good way or in a bad way, the performance of the system. Okay, so remember, I was trying to predict the number of jobs, how the number of jobs in the US changed during the recession time in 1980. So in the left side, we can see that I was using the 3 models that I said, the bathtub, mixture, and covariate. But the bathtub and mixture is pretty bad. And the covariate model is actually the black line over there. It's tracking very well the orange line, which is the actual data. Okay. And then in the right side, I'm just showing the confidence interval as well of the covariate. So you can see that just one single point was outside the confidence interval. And I have the goodness of fitness over there. And again, in bold, I'm showing the good ones. So its covariate model is way better than the other 2 approaches. Okay. So I'm also computing the area under the curve that I said. So I'm computing for the actual data and for the predict data that I showed you using the model. And again, we can see that the relative error between the actual and the predict data, and the difference, the relative error was way smaller using covariate models. So we can conclude that covariate is better than bathtub and mixed distribution. So again, to conclude, I was presenting 3 different approaches to predict system performance. So we can basically predict recovery time. But we can see that by including external information of activities that impact the system, we can actually predict better how it changes over time. And we can also predict better the area under the curve. So for future research, I'm also going to apply time series models and optimal allocation to actually decide how much effort, how much to spend at each activity to improve the performance targets that I want. That's all. Thank you.